Welcome to The Explainer. Today, we're diving into what is basically a scientific detective story. It's about this really clever trick that could totally change how we build electronics.
All right, so let's just jump right in. How do you do this? I mean, it sounds completely impossible, doesn't it? It's like trying to build a perfect Lego tower on a pile of sand. But believe it or not, a team of scientists actually pulled it off. And they did it with probably the most important material in all of modern technology: silicon.
So, silicon, it's the absolute bedrock of our digital world. But it's got this secret flaw. The second it even touches air or water, bam, it instantly grows this messy, chaotic layer of oxide, kind of like rust.
And right there, that's the heart of the puzzle. See, to build the next generation of electronics, you need these perfect, orderly, crystalline layers on top of the silicon. But silicon? Oh no. It insists on covering itself with this bumpy, messy, amorphous oxide layer first. It's like it's working against us. Now, this idea of perfect growth, it actually has a name. It's called epitaxy, and it is the absolute gold standard for making high-quality electronics. The problem is that messy oxide layer, well, it should make epitaxy on silicon totally, completely impossible. And yet, they did it. Even the scientists themselves called it an unexpected result. So how in the world did they solve this impossible puzzle? Okay, let's start digging into the clues.
So, what was the setup for this incredible experiment? Well, forget about these billion-dollar ultra-sterile clean rooms you might be picturing. This breakthrough, it happened in a simple beaker. Yeah, a beaker. They used a technique called electrodeposition.
Okay, so after they ran the experiment, the very first clue they got was, honestly, it was stunning. They looked under a microscope and saw a surface covered in these tiny little pyramids. And get this, they were all pointing in the exact same direction. That's a huge hint that the film they grew wasn't messy at all. It was super, super ordered.
But how ordered are we talking? To really find out, the investigators, the scientists, they brought out the heavy-duty tools. They used X-rays to get a kind of atomic fingerprint of the structure, and what they found was a fantastic twist in the story. So here's the fundamental problem, right? The spacing between the atoms in silicon and the atoms in the cuprous oxide they were growing, it was off by a whopping 21.4%. I mean, to put that in perspective, that's like trying to stack Legos perfectly on top of Duplo blocks. They don't fit at all. But the X-ray fingerprint revealed something absolutely brilliant. The cuprous oxide crystal had, all by itself, spontaneously rotated exactly 45 degrees compared to the silicone underneath. Now, why on earth would it do that? Well, it turns out it was a genius move. That one simple twist completely changed the atomic alignment. It slashed that impossible mismatch down to a much more manageable 11.2%. It's incredible. The crystal literally found a way to make itself fit. Okay, so that solves one mystery, but it just opens up an even bigger one. Think about it. How could the crystal possibly know which way to orient itself if there was a layer of that random messy oxide blocking it from the perfect silicon template underneath? It shouldn't be able to see the pattern. The final piece of the puzzle came when they brought in the big guns, a high-resolution microscope that could literally see individual atoms. And there it was. The scientists had finally found their howdunit. The images showed the smoking gun. There were these tiny, tiny regions, we're talking just 10 nanometers wide, where the cuprous oxide had punched right through the messy oxide and formed a direct bridge to the silicon. These little seeds, they were the key to everything. So here's how the whole ingenious trick works. It's a three-step process. First, these tiny, perfect crystal seeds form, and they anchor themselves directly onto the good silicon. At the same time, that messy oxide layer forms around them. Then, the main growth process kicks in, and it uses those perfect little seeds as the foundation. And finally, and this is the coolest part, the crystal grows upwards and sideways, building a bridge right over the messy oxide stuff to form one single, continuous, perfect film. It's exactly like putting a few stable Lego base plates on that pile of sand before you build the rest of your tower. Okay, so, a brilliant solution to a really tough puzzle. But what's the big deal? Why does any of this matter? What can we actually do with this new trick?
Well, this technique gives us a whole new toolkit for making electronics. For one, this overgrowth method lets you create these beautiful, defect-free films. It also means we can combine materials with huge mismatches that we couldn't before. And this creates something called a semiconductor-on-insulator structure, which is a super powerful way to make faster, more efficient chips. And maybe the best part, it's all done in a beaker. It's simple and cheap, not in some crazy expensive vacuum chamber. And when you start thinking about the potential applications, wow, it gets incredibly exciting. We're talking about things like high-efficiency solar cells, brighter LEDs and lasers, maybe even advanced materials for spintronics or epitaxial nanowires. You could even integrate new and interesting oxides with silicon. The door is just wide open now.
You know, the really crucial takeaway here is this. By understanding what we thought was a material's weakness, in this case silicon's annoying habit of creating that messy oxide, we can actually turn it into a strength. We can use it to our advantage. And that opens up a whole new way to engineer the future, one atom at a time. It really makes you wonder, doesn't it? What other impossible things are we going to build next?